Welcome students. In previous class we saw how to find out certain integrals which were involving polynomial expressions. We looked for the integrals at the later half of the class of the kind px plus q over ax square plus bx plus c, px plus q over square root of ax square plus bx plus c, and as a particular case 1 over ax square plus bx plus c and 1 over square root of ax square plus bx plus c. All these integrals we converted into certain known forms, and we try to evaluate them using those known forms. Before moving further, I will pick a couple of more examples. One example related to this particular form to further understand or for how to apply the methods which we learned. So, we will pick one quick example here. We need to integrate 2x minus 1 over square root of 4x minus x squared. So, if you compare it with the form px plus q over square root of ax square plus bx plus c, notice that here a is negative minus 1. So, as in previous class I told you, in order to evaluate this, what we do is that we write the numerator in terms of a specific combination of the derivative of the denominator plus a constant. So, we will write it 2x minus 1 is equals to a times d by dx of the denominator function except the square root. So, here it is 4x minus x squared plus b. So, that we will get a times 4 minus 2x plus b. Now, both sides are polynomial, therefore, we can compare the coefficients. So, first compare the coefficient of x. So, you get 2 equals to minus of 2a, implying that a is equals to minus 1, and then 4a plus b equals to minus 1, implying that b equals to 3. So, once we got the values of a and b, we replace this 2x minus 1 by this expression in the integral. Let us say this integral is I. So, the integral I now, after replacing this term, can be represented as a times d by dx, which is 4 minus 2x, sorry, instead of a I have to put it minus 1, minus 1 minus 1 times 4 minus 2x, and plus b, the value of b is 3, divided by square root of 4x minus x squared dx. This is minus 1 times 4 minus 2x. I can write it as 4 minus 2x divided by square root of 4x minus 2x dx, plus the next term is 3 integral dx over 4x minus x squared, square root of 4x minus x squared. Look at these two parts here. So, in earlier case, when the square root was not there, we substituted 4x minus x squared, 4x minus x squared. So, in earlier case, when this square root was not there, we substituted this term, so that it became 1 by t. So, we shall do the same process, and let us see what it evolves to. So, 4x minus x square equals to t. So, that 4 minus 2x dx equals to dt. So, in the first integral it turns out to be minus of integral dt over square root of t plus 3 times the second integral. Now, in order to evaluate this, what we do is that it is of the form ax square plus bx plus c. So, we will try this is of the first form which we discussed in the previous class. This is of the form 1 by square root of ax square plus bx plus c. So, we will try to make a perfect square out of it. So, you can easily see that I can write 4x minus x square as minus of x square minus 4x, which I can further write as 4 minus x square minus 4x plus 4, which will make it 4 minus x minus 2 whole square. So, the term 4x minus x square now converts into the form 4 minus x minus 2 whole square. This dt by root t can be easily evaluated. It is basically t raised to power minus half. So, which will give you t raised to power half divided by half plus 3. This integral, if I put x minus 2 equals to u, then dx is equals to du. So, that this integral will be converted into the form of du over square root of 4 minus u square, which if you remember the formula, this is of the form a square minus u square. So, ultimately this turns out to be minus of 2 square root of t plus 3 a square minus u square. So, this will be sin inverse u by a, so u by 2 plus constant. Finally, substituting the values of t and u, we will get minus of 2 square root of t, and t is nothing but 4x minus x squared plus 3 sin inverse u is nothing but x minus 2 divided by 2 plus a constant of integration. So, we note that the integration of 2x minus 1 divided by root of 4x minus x square gives us this integral value. What is more important here is to understand how we proceeded by converting into two separate integrals, for both of which we knew how to evaluate this. The idea that we proceeded here for this particular problem, writing the numerator as a combination of a derivative of the denominator, this can even be further used for the cases where the denominator, which is a quadratic term, is having a degree other than half. For example, so far we have considered these two cases where the denominator ax square plus bx plus c is having a degree 1 here, or the entire term was having degree half. Square root means having a degree half. So, if other than that, if it is some other term also, say for example, it is ax square plus bx plus c raised to power some 3, 4 or some other number, then also you can use the same idea, writing px plus q as a combination of this denominator, derivative of the denominator plus some constant, and then you can proceed further. We will pick another quick simple example. So, let us find out the integral of x square over square root of x raised to power 6 plus a raised to power 6, where a is some constant which is given to be positive, and we have to find out this integral. Look at this integral carefully. So, we have to find out. Well, I hope you would have quickly noticed that this integral can be represented as x square dx over square root of x cube squared plus a raised to power 6. And if I take the derivative of x cube, I will get x square, which is part of the integrand. So, taking x cube is equals to a new variable t, the rise of x square dx turns out to be equals to dt, and therefore, this integral will be converted into form of 1 by 3 dt over square root of t square plus, since I want to use my formula which I already know of the form x square plus a square kind of formula. Therefore, this a raised to power 6 I should write as a cube squared. So, this becomes very easily the known form of integral dt over t square plus, if I consider this a cube to be some new number a, then this is t square plus a squared. So, for that integral of t square plus a square, we know it is nothing but logarithmic of t plus a square root of t square plus a squared, that means a cube squared plus constant, which finally gives us 1 by 3 log of what is the t? It is x cube plus x cube squared, a cube squared plus constant. So, noticing a small thing here that a 6 can be written as a cube raised to power 2, we can simply solve this example. So far we have seen that certain integrals which were written in certain algebraic form can be evaluated using these techniques which we have developed. Further, now we shall look at another method which is known as method by partial fraction. So, if we are given the integrand, this is of the form px by qx dx. So, we are going to look for the integrals of this kind. So, our integrand is of the form px by qx such that qx is not equals to 0, that means it is a rational function of p and q, where p and q are polynomials in the variable x. So, in order to use method of partial fractions, we shall assume certain specific forms on these p and q. The degree of a polynomial is defined as the highest degree term present for the variable. For example, x square plus 3x plus 4, if I define it as a px, then this is said to be of degree 2 or a quadratic polynomial. Similarly, if I define an expression in cube, then that will be defined as cubic. I hope you all are aware of that. So, if degree of the polynomial Px is less than degree of the polynomial Qx, then the rational function P by Q, we call it as proper, and if it is not so, if that degree is bigger than or equals to degree of Q, then we call it improper. So, for a proper rational function, the degree of Px should be less than degree of Qx. One important fact one can note that even if it is improper, say for example, degree of Px is larger than that of Qx, we can use large division and then we can further write it as a polynomial plus another rational functions which will be a proper rational function. I will show you with the help of an example how it can be done. So, for method of partial fractions, what we assume is that the denominator polynomial Qx can be factorized into either linear or quadratic polynomials. That means, we can factorize this Qx in terms of linear factors, or if not, then at least in quadratic polynomials. One such examples we have already seen in previous class was when we were evaluating the integral of dx over x square minus a square. So, here if you look at it carefully, the integrand is of the form p by q, where p is equals to 1 and q is equals to x square minus a square. Also, q can be written as x minus a times x plus a, and therefore, q can be factorized in terms of two linear polynomials making q. So, depending on the specific forms of p and q, we can assume specific partial fractions. So, forms of the rational function and the partial fraction we should choose for that. So, if the form is linear in the numerator and the denominator which is quadratic can be written as factor of two different linear factors, a not equaling to b. Sometimes if we put this Qx to be equals to 0, this a and b are also called roots. So, in that sense we can say that the denominator function has two distinct roots, a and b. So, in that case we choose partial fraction as a upon x minus a plus b upon x minus b. Similarly, if the case is of repeated root, numerator function is of the form px plus q and denominator is repeated, that means x minus a squared. In that case, the partial fraction is chosen as a upon x minus a plus b upon x minus a whole squared. So, these are the two cases for the case when numerator is linear and denominator is quadratic. If the denominator is a cubic function, then suppose that there are three distinct roots. And numerator is a quadratic polynomial. then the partial fraction corresponding can be given as so A is not equaling to B, none of the A, B, C are equal, A not equals to B and B not equals to C and A not equals to C. So, fourth case again, since it is a cubic polynomial in the denominator, therefore, there is a possibility of two repeated roots. So, p x square plus q x plus r over x minus a whole square into x minus b. In that case, I can write it in this fashion, x minus a plus b for the repeated root case x minus a whole square. So, this is similar to the previous case when we had a repeated root case here, plus c upon x minus b, and fifth case when numerator is quadratic, p x square plus q x plus r and denominator is of the form x minus a into a x square plus b x plus c. That means, it cannot be factorized into the linear factors. In that case, the choice is a upon x minus a. So, the linear factor separate plus corresponding to the quadratic factor, which cannot be further factorized into linear factor, the choice for partial fraction will be b x plus c by a x squared plus b x plus c. Oh, let me call it as a 1, so that there is no confusion, a 1, the two terms are different, a and a 1. So, it has a distinct root here, and these are the coefficients of the polynomial. So, these are 5 specific cases corresponding to which partial fractions are written, and in the similar process, in the similar way, we can define further partial fractions for other expressions as well. So, if roots are distinct, then we write them separately. If roots are repeated, then the term is written once again with the quadratic term as well, and similarly, if there is a quadratic term which cannot be further factorized, then corresponding to that, the term is written as a multiple of the variable x plus constant. So, these forms one has to keep in mind. So, let us choose the example of one integral which we have already done is dx over x square minus a square. So, we already know the value of this integral as 1 by 2a log of x minus a over x plus a plus constant. So, what if we solve it using partial fractions? We can see that the denominator function here can be factorized into x minus a into x plus a. So, the entire factor can be written as equals to the partial fraction of this rational function is noted down as a upon x minus a plus b upon x plus a. So, the form of the integrand, if it is of this form p x plus q upon x minus a x minus b, they should be written as a by x minus a plus b by x minus b. So, here the integrand is of the form 1 by x square minus a square, which I have written in this form. So, this should be written as a upon x minus a and plus b upon x minus b. So, computing this, we can find that taking x minus x plus a again as LCM here on the right hand side. So, what you get on the right hand side is a times x plus a plus b times x minus a, and on the left hand side you will get 1 because x minus a x plus a is cancelled throughout. So, you compare the coefficients, again being the polynomial, you compare the coefficients of both the sides. So, what you should get is a plus b, the coefficient of x on the right hand side, and there is nothing on the left hand side, therefore, a plus b equals to 0, and here a minus a b. So, a can be taken as common, equals to 1. So, from this expression we can figure out that a equals to minus b, and if I substitute a is equals to minus b here, what I get is that minus 2 a b equals to 1, which will give me b equals to minus 1 by 2 a. Since a is equals to minus b, therefore, a is equals to 1 by 2 a, and therefore, this expression, the integrand is written to be equals to a is 1 by 2 a, 1 by x minus a, b is 1 by 2 a with a negative sign. So, minus, I can take 1 by 2 a as common, 1 over x plus a. So, if you remember, you found the same thing when we derived this formula in our previous class. Now, you can easily write this 1 by 2 a, this is logarithmic of mod x minus a minus logarithmic of mod of x plus a, and then plus a constant c. So, log of m minus n is same as log of m by n, and therefore, the same formula we will reach to. So, we will give you another example here. Suppose that we want to integrate the function dx over x into x raised to power 4 plus 1. So, this does not fall into any of the form which we have discussed so far. So, but if we do some change in the integrand, we can see that we can actually find out the integral using partial fractions. So, for that, what we have to do here is that we try to figure out what if we substitute some number, so that your substitution as it used to work, that you get a factor of the integrand in that derivative. So, here it is x raised to power 4, here it is x. So, none of them are working, but if we multiply it by x cube, in both numerator and denominator, what I will get is x 4 plus 1. Well, now, if I substitute x 4, then I see that x cube dx, that is appearing there. So, a factor of the integrand is appearing in the numerator. So, that substitution I will make x raised to power 4 is equals to t, which will make 4 x cube dx is equals to dt. So, that x cube dx is equals to dt by 4. So, this calculation leads to 1 by 4 of dt over t into t plus 1. This integrand now is of the form which we are looking at. So, quadratic in denominator and constant in the numerator. Therefore, I can make partial fraction out of it, 1 by t into t plus 1. I can write it as a by t plus b by t plus 1. So, now I just need to compute the values of a and b, again using the comparison, a time t plus 1 plus b time t. So, it will lead to a is equals to 1 and b is equals to minus 1. So, that this integrand can be written as 1 by 4 integral dt over t plus 1, this number can be replaced by this number a. So, 1 by t b is minus 1, therefore, 1 by t plus 1 dt, which one can see very easily is 1 by 4. 1 by t dt is log of mod t minus this is log of mod t plus 1 plus constant. So, substituting the value for t, which is x raised to power 4, we get final answer as 1 by 4 and also using the formula simultaneously log of m minus log of n is equal to log of m by n as x raised to power 4 divided by x raised to power 4 plus 1 mod plus constant c. So, this is what you get. So, as I mentioned, the case for the rational functions which are of the form p x by q x such that q x is not 0. It may be possible sometime that degree of p x is more than degree of q x or equals to the degree of q x. In those cases, what we do is that we first do the long division, so that we get a polynomial and then a proper rational function, and then on that rational function we apply partial fractions. So, let us look at one example. Which will help you to understand the problem. So, the example is x square plus 1, x square plus 2, x square plus 3, x square plus 4 dx. We need to evaluate this integral. If you look at this integrand, it looks like x square times x square x raised to power 4. So, it is a 4 degree polynomial in the numerator, 4 degree polynomial in the denominator. But if we also look at it carefully, we can see that the quadratic terms, they are only appearing in both the numerator and denominator. There is no linear term or there is no cubic term. So, no other term is appearing there apart from these quadratics. Therefore, what we can do is that before beginning to find out the solution of this problem, we can simplify this expression by substituting it as a new variable x square equals to y. So, we are not making it as a real substitution in the integral, rather we are just making this substitution in integrand. So, the integrand becomes this integrand becomes y plus 1 y plus 2 over y plus 3 into y plus 4, which makes, if I look at the product, y square plus 3y plus 2 divided by y square plus 7y plus 12. So, both the numerator and denominator, they are having the same degree term, and therefore, we have to go for the long division. So, let us divide y square 7y plus 12 y square plus 3y plus 2. So, the coefficient is same here, therefore, it can go one time. So, I will get here y square plus 7y plus 12. Subtracting, we get these signs as minus. So, what is left here is that this y square get cancelled, 3 minus 7 will give you minus of 4y and 2 minus 12 is minus of 10. So, the remainder here is minus 4y minus 10. So, this expression of integrand, this expression of integrand can be written as 1 plus minus of 4 y minus 10 divided by y square plus 7 y plus 12. This is what the integrand is. So, we will write it now, the integrand this fashion, or we can further write it as 1 minus, instead of 1 plus 1 minus 4 y plus 10 by y square. So, this factor can further be written as, y plus 3 into y plus 4, and this is for the integrand. So, our actual integral I, which is x square plus 1 x square plus 2 divided by x square plus 3 into x square plus 4 dx. In this we only changed x by y, x square by y. You see here, we just change x square by y. Therefore, let us go back in order to write that integral. So, in this integrand, replace y by x square. So, this will be equals to 1 minus 4 x square plus 10 divided by x square plus 3 and x square plus 4. dx. So, now this entire exercise of solving this expression converts into another problem, which is having 1 as a polynomial and then another expression. So, what we will do here is that further is that we know how to handle this expression now, because this integral we can handle using partial fraction. So, in order to solve this, we will go through partial fractions, and I will show you how to find out the partial fraction for 4 y plus 10 upon y plus 3 into y plus 4. So, the partial fraction for this will be written as a y plus 3 plus b y plus 4, which you can easily, after solving, you can find out that in this case a turns out to be minus 2 and b turns out to be 6. So, take the multiplication, do that, and then you can write this calculation. So, you will find out that a is equals to minus 2 and b is equals to 6, and hence this integral will be equals to integral 1 dx minus this factor, replacing y by x square is same as this factor. So, will be a, which is minus 2. So, minus of, let us put a curly bracket here, minus 2 upon y plus 3. So, y replaced by x square plus 3 integral dx plus b. So, plus 6 by y plus 4 x square plus 4 integral dx, and then curly bracket closed. So, what we have done so far is that this expression has been converted into, using some new replacement y, converted into this expression, and corresponding to this we have used the partial fractions, and now we have written this expression in terms of those partial fractions. So, ultimately the integral which finally equals to this integral leads to, I will rewrite it, equals to integral 1 dx, which is nothing but x plus 2 times 1 over x square plus 3 minus 6 times integral 1 over x square plus 4 dx dx. So, this expression can be easily evaluated as x minus 2 times x square plus a square, the formula. This will give you 1 by a tan inverse x by a plus 6 times, this will also give you 1 by a tan inverse x by a plus constant. So, after simplification this goes to 2 3 6. So, this will be a form of solution which you can get. So, sometimes it helps if instead of looking at the problem exactly the way it has been written from a different perspective, by replacing or changing some variable, it may become far more easier to solve using the methods or the techniques which we know. In the next, we will look for another example of another kind. So, this example deals with the problem of linear factor in the numerator, and the denominator is a cubic polynomial having 2 as a root and then x square plus 1 as a factor. So, suppose that we are to find out this integral. So, as integrand one can see that this is of the form linear divided by cubic, where the cubic is having one linear factor and the other quadratic factor. We again go back to the form of the partial fractions, where it was mentioned that in case if the quadratic factor cannot be further factorized, then in that case we have to write it as the linear factor plus bx plus c times quadratic factor. So, this case can be compared that p equals to 0, q and r both are 1, because this is 1 and 1, q and r are 1, and similarly we can compare other coefficients to write this. So, the integrand written as partial fractions will be written as a upon x minus 2 plus bx plus c upon x square plus 1. So, simplifying this, we get left hand side as a linear polynomial, right hand side we get a x square plus 1 plus bx plus c times x minus 2. So, you can see there a x square and here you will get bx square. So, a plus b, since on the left hand side there is no x square, therefore, a plus b equals to 0. Once you compare the coefficient of x, what you will get from here is that minus 2b plus c. So, minus 2b plus c, the coefficient of x here is 1, and then further if you compare the constant coefficients, it gives you a minus c minus 2c, a minus 2c on the left hand side equals to 1 on the left hand side. So, we get these 3 equations, 3 unknown, 3 equations. So, you can solve them. Clearly, a is equals to minus b, therefore, either you substitute b is equals to minus a or a is equals to minus b, and then you solve these 2 equations in either in a and c or b and c. So, it should not be very difficult for you to solve and figure out that a is nothing but 3 by 5, b is nothing but minus of 3 by 5, and c is nothing but minus of 1 by 5. So, the integrand can be represented in this factor form, and therefore, the integral I shall be represented as this factor is equals to a, where a is equals to this number, b and c are these numbers. So, we will replace this integrand with this factor by replacing values of a and b also. A is 3 by 5. So, it is 3 by 5 of 1 over x minus 2 here, plus b is minus 3 by 5. So, minus 3 by 5 times x plus c is minus 1 by 5 minus 1 by 5 divided by x square plus 1 dx. So, this entire integral now turns out into this form. The first factor integrating it is very easy. In order to integrate the second factor, what we do is that we break it into two parts. So, the integral we shall write as following: 3 by 5 integral of x minus 2 minus, I can take 1 by 5 as common, integral of 3x over x square plus 1 and then minus dx, of course, 1 by 5 1 over x square plus 1 dx. So, this is what we will get, minus 3 by 5 minus 1 by 5. So, the integral turns out to be 3 by 5 log of mod of x minus 2 linear term minus 3 by 5 this x square plus 1. If I replace it by a number t, then I will get 2 x dx is equals to dt. Therefore, x dx will be dt by 2. So, I can immediately write it as 1/2 of logarithmic of mod of x square plus 1. So, now you can evaluate it simply, minus 1 by 5. So, here it is dx over x square plus 1, which I can immediately write using the formula tan inverse x, and plus finally a constant of integration. Simplifying it a bit here, you can get the final answer. So, the cases where the function cannot be factorized further, for example, here x square plus 1 cannot be factorized further, we can use this technique and find out the integrals using some other known formulas. This topic of partial fraction, this can further be practiced, and when you solve problems you will realize that how to compute the values of a, b's and these unknown constants, and once you are able to factorize them in terms of linear or quadratic factors, the formula which we have already developed, they become very handy. So, evaluating those integrals which are of the form p by q, where those p by q can further be written in terms of partial fractions, it becomes very easily. Next, we shall look for another kind of method which is known as integration by parts. This method is important when we have to solve the integrals which involve certain products. So far we are seeing that integrands are becoming complicated. When they involve certain products, sometimes it becomes easier if we are able to break them into products and find out the integrals of those. So, further we shall look another method for evaluating the integrals, where the integrand is given as the product of certain functions. Sometimes it becomes easier if we know the integral of the parts, or if we can convert them into a certain form where we can evaluate the integrals of the parts, then this particular method becomes very useful. So, we shall look at the method known as integration by parts. The method is motivated by the fact that in case of differentiation, we know that the differential of two functions u and v, if we take the differential of their product, it turns out to be where u and v are obviously assumed to be function of x. If we integrate this throughout, so we know we can operate this integral operation, we get u v equals to integral of u dv over dx plus integral of du over dx times v dx. Now, if I write this expression by taking this u dv over dx on the left hand side and write it as uv, then it becomes minus of du over dx times v dx. Now, make certain assumptions here. Assume that u is a function of x f x and v is a function of x such that dv over dx is equals to g x. You will notice why we are doing this. So, that what it will come here is that f x dv over dx is g x. So, f x times g x dx. Then this expression will take the form as integral of f x g x dx equals to u v. So, u is f x, dv over dx is equals to g x. Therefore, v will be integral of g x dx minus integral du over dx, since u is equals to f x. Therefore, du over dx will be f prime x times v is again integral g x dx, put a close bracket and then entire integral. So, integral of this entire thing. So, what we notice from here is that if we take this differentiation of the product of two functions, we use that formula, where we ultimately reach to using these two functional identification, we reach to this formula, integration of functions f x g x dx is equals to f x integration g x dx minus integration f prime x into integration of g x dx and then the integration of the whole. So, this becomes the formula for integration by parts or formula for integration of product of two functions. How shall we understand it? So, integration of the product. So, we will call one of the function as first function and other function as second function. So, if the integrand is written the product of two functions first into second, then integral equals to, we are calling f x as first function, we normally memorize or remember it in this form, multiplied by g x dx integral, that means integral of second function minus integral f prime, that is differentiation of first function multiplied by integral of second function. So, the integration of the product turns out to be first function integral of the second function minus integral differentiation of the first function into integral of second function. Let us look at one quick example which will help us to understand this formula. Very simple example. To evaluate x e raised to power x dx. So, in order to evaluate this, we can choose a function as first function. So, suppose that we choose this as first function and this as second function. Then what does formula say? First function x integration of the second e raised to power x minus differentiation of the first x prime. So, dx prime is 1 multiplied by integration of the second is e raised to power x, integral of whole, and therefore, this gives you x e raised to power x minus exponential integral is again e raised to power x and plus finally a constant of integration. So, this is the integral in this case using this formula of integration by parts. What is important, or you may note here, is that whenever we are integrating first during use of the formula, we are not using constant. Let me put it here for you and see what happens. So, suppose that during the process of integration, if we have used the constants, then the integral of x e raised to power x dx would have taken the form of first function, this is first function, this is second function, into integration of the second. So, instead of writing e raised to power x, I should have written here e raised to power x plus c minus integration differentiation of the first function, it will be 1, again integration of the second, I should have written e raised to power x plus c, then dx. So, ultimately what I will get here is that x e raised to power x plus c x minus integral of this term now is e raised to power x because of this factor, c is a constant. So, integral will get me c x plus another constant c 1. This c x cancels with this c x. So, ultimately I get x e raised to power x minus e raised to power x plus a constant c 1. You know that up to constant these are fine. So, these two integrals are same. So, it is redundant to write the constant during the process of integration and we can leave them. So, we do not bother when we are writing the integral of the second function, and at that time we leave those constant. It is very important to choose here or make the choice of the function, that which function should be chosen as first function and which function should be chosen as second function. If you look at the formula for the product, this formula becomes very handy if we have a proper choice of the functions. If you notice carefully in the formula, what is happening here is that the product function is going to have the integral of the second function and the differentiation of the first function. So, if we have a function which reduces when we take the derivative, say for example, a polynomial function, you know that if you differentiate polynomial function, its degree reduces, then we may choose that polynomial function as a first function and other function as second function, but that cannot be considered as rule. It depends on what is our second function, because if we have a second function as a function which will be giving or the function for which we do not know the integral, then it will be difficult for us to evaluate that integral. So, we shall look for the choice of these functions, that which function we should choose as first function, which function we should choose as second function, also how we should make use of this particular formula in our next class.